Hi, I'm Liz Rice. I look after open source engineering at Aqua Security, where we specialise in cloud-native security tools for enterprise. I'm also an AWS container hero and the author of a book about container security. And if there's one thing you can do to improve the security posture of your Kubernetes applications, you get a lot of bang for your buck with vulnerability scanning. So I want to talk today about why it's important and how you can build vulnerability scanning into your workflow. We'll start by reviewing what kind of vulnerabilities we're talking about and what a container image scanner does to identify vulnerabilities. And then we'll look at a number of options for automating image scanning into the lifecycle of a container image that's being deployed into Kubernetes. A vulnerability is a weakness or a flaw that a bad actor can take advantage of to do something unexpected in your deployment. It might be a bug, it might be missing validation in a piece of software. And there's a whole industry around security research where people examine software trying to find these vulnerabilities. If they're responsible researchers, they report them so that the vulnerability can get fixed and everyone can upgrade their version of the software package to run with the fixed version. If you don't have the fixed version, you're running with the vulnerability, and an attacker might be able to take advantage of that to steal data or tamper with your deployment. Some famous and serious vulnerabilities get logos and brand names. You might have heard of Meltdown, Shellshock, Heartbleed, and Dirty Cow. These are just the tip of the iceberg. There are thousands of known vulnerabilities, and new ones get published every day. Most application software uses some dependencies, and there's a very good chance that your applications that you're running today use dependencies that include some vulnerabilities. Hopefully none of these four, but if you're not checking, you don't know. So that's why you really should be scanning your container images. The primary source of information about which software packages have vulnerabilities is the National Vulnerability Database, or NVD. Every vulnerability has an identifier called a CVE, it stands for Common Vulnerabilities and Exposures. And the NVD maps between CVE identifiers and the software packages that have that vulnerability. Let's take a look at an example. Doesn't really matter what this particular vulnerability is, but here we can see NVD's telling us that this vulnerability exists in all the versions of the Varnish HTTP cache between 4.1 and 5.2. So a basic vulnerability scanner might check whether you have a version of this package within that range installed, and if you do, it would tell you that you're vulnerable. Let's imagine that you're using Varnish 5.0. Based on this information, you could imagine that you have that vulnerability, but it might not be as simple as that. Different Linux distributions handle security patches in different ways. Taking Debian as an example, rather than upgrading to a whole new version of a package, they choose to back apply security patches individually to whatever version is current for a particular distribution. So if you were running that Varnish 5.0 package, but your distribution was Debian Stretch, as shown here, you might have a patched version 5.0. NVD doesn't know about these distribution-specific patched versions. So unless your scanner looks at the Debian security advisory like this one, it would report a false positive. So a vulnerability scanner needs to know about vulnerability information, not just from NVD, but also from any distribution-specific security advisories. The job of a container image scanner is to look at all the software in an image and report on the vulnerabilities that are present. And you need to run this on every image because every image is different. They're typically, not always, but typically based on a Linux distribution. It might be Ubuntu or Amazon Linux or Alpine. You need your scanner to support all the distributions that your images are using. Software is typically installed into the image at build time using a package manager, and the package manager typically depends on the distribution. The scanner needs to support the package manager so that it can find all the right version information. And vulnerabilities don't just exist in these operating system packages, they also exist in language-specific dependencies and libraries that your application might use. For example, if your app's written in Node, it's very likely it depends on packages installed using npm. If you're using Python, the installer might be pip. So language support is another thing to look out for when you're choosing a vulnerability scanner. To make this more concrete, let's look at the results of scanning an image that has some vulnerabilities. I'm going to show you some output in human readable table format. Typically, scanners also support machine readable formats like JSON as well. Here I'm using an open source scanner that's maintained by my team at Aqua called Trivy. I've run Trivy on a fairly old Nginx image, and it's found some significant vulnerabilities. It's found 1 critical and 32 high severity issues here. One interesting thing to note is that in many cases, the fixed version column is empty. So at the time I ran this check, there wasn't a patched version available for some of these packages. If you find a serious vulnerability with a patch, it's fairly clear that your path of action is to rebuild the image with that patched version. But you probably want a policy on how you handle vulnerabilities where there's no fix available, and how you're going to decide whether it's safe for you to use this image or not. Some scanners, Trivy included, have an option to only show fixable vulnerabilities and to ignore those that don't have fixes on the basis that you only show the actionable vulnerabilities. This screenshot shows what it's like to run a scanner manually, but in practice, you want to automate scanning during the life cycle of your application images. And there are several different places where you might want to do this. You can scan an image as soon as it's built as part of the CI pipeline. It's also a good idea to keep scanning your images regularly in case new vulnerabilities get discovered in existing code. So you might want to scan regularly everything that's in your image registry. At the point where you're deploying a workload to Kubernetes, you might want to check that it's been scanned and that it's safe to deploy. And finally, you might want to be able to check the vulnerabilities that are currently present in your running workloads. We'll take a look at some examples of scanning in all these different stages of the lifecycle. For the best view of your vulnerability posture, you do scanning at all these stages, but it's up to you whether you consider them all essential. And there's not a lot of point in doing the scanning unless you have a process or a policy for acting on the results. So let's quickly run through how you can, in practice, automate scanning at these different stages of the life cycle, starting with scanning during the build pipeline. You can run vulnerability scanning as a build step, just like you might run a test as part of the build pipeline. Here's an example of Trivy built into AWS code build. It's set up to fail if the scan reveals any high severity or critical vulnerabilities. And in this example, it did find one, so the build step failed. The container image never got pushed to the registry, and there's no chance of deploying this vulnerable image. But as I mentioned, because new vulnerabilities get uncovered every day, it's possible that a new vulnerability might get discovered in the image after it's been pushed to the registry. So it's a good idea to have regular scanning built into the registry. As an AWS user, the easiest way to do this is to enable scanning in ECR. It's as simple as flicking a switch for the image repository. There are also commercial container scanner solutions that will integrate into ECR and other registries out of the box. And you'll get a nice report like this in the console showing you the vulnerabilities. Now, if you're really eagle-eyed, you'll see that this is an Nginx image. And in fact, it's the same image that I scanned with Trivy on the command line earlier. And I did these scans only a few moments apart. But if you remember, Trivy found a critical issue and over 30 high severity issues. So these results look completely different. They look really different at all levels of severity. ECR is using another open source vulnerability scanner called Claire. And as you can see, Trivy and Claire are showing totally different results for the same image on the same day. This is one of the problems with vulnerability scanning. If you see results that look so different like this, how are you going to trust the scanners at all? There is a reason for this, but you need a bit more knowledge to make sense of results like this. To illustrate it, let's take a look at the CVE that Trivy identified as critical. Here it is, and I've also shown the same CVE in the output from Claire in the ECR console. It's the same vulnerability, it has the same identifier, and both scanners are reporting it in the same version of the same package. The difference is that Trivy says it's critical and Claire says it's medium severity. So which is right? Let's look up this particular vulnerability on NVD and find out what it says about the severity of this issue. And here we'll find the explanation for the discrepancy. And it comes down to the way that vulnerabilities are classified into different severity levels. This classification is done using something called CVSS, the Common Vulnerability Scoring System. And if you look at NVD, you'll see information for two different versions of CVSS, the older version 2 and the more up-to-date CVSS version 3. Both these versions take some characteristics of the vulnerability, like whether it can be exploited remotely, how easy it is to exploit, and other characteristics. And they use a formula to turn those characteristics into a score, and from that score into a severity for the vulnerability. And as you can see, for this particular vulnerability, under the newer V3 system that Trivy uses, the vulnerability is classed as critical, whereas under the older V2 system, it was only classed as medium. So in a way, both the scanners are correct. They're just using these different scoring systems. You can also find discrepancies based on where different scanners get their vulnerability data from, how often it's updated, whether or not they're showing vulnerabilities that don't have fixed versions available. Now, if you end up using more than one scanner in your system, you'll need to know things like which version of CVSS they're using, so that you can know whether it makes sense to compare their results, whether comparing results from the two different scanners is really like comparing apples with apples. The next place where you might want to automate a check on an image during its life cycle is at the point where you're about to deploy it to Kubernetes. And Kubernetes gives us a really nice opportunity to do this by implementing what's called an admission webhook. This gets called whenever a new resource is deployed. There are two forms of this webhook. One's called a validating webhook, and it returns a yes or no answer as to whether or not Kubernetes can proceed with deploying this resource. And there are also mutating webhooks which can change the definition. For our purposes today, let's just consider a validating webhook. In AWS, you might set up something like this, where the validating webhook triggers a Lambda function that determines whether a pod is okay to deploy or not. I adapted this diagram from a nice post on the AWS blog that goes into more detail on how to implement something like this, and I'll share a link at the end of this presentation. The check image Lambda function might trigger a scan, but that would potentially delay deployment because even the most efficient of scanners can take a few seconds unless they have a cached result. So you might want this function to check that the image has already been scanned in the recent past and that the results didn't contain anything untoward. The blog post that I mentioned assumes that you'll get this information from the ECR Claire scan results. But if you're using a third-party integration, you could get results from another scanner instead. It's worth noting that a pod can include multiple containers, but the webhook only gets called once per resource or once per pod. So your check image function would need to validate all the container images that are included in that pod spec. Now, let's suppose your images passed the checks and they were deployed successfully into the Kubernetes cluster. Now they're running live, but what if you want to check for vulnerabilities in your running workloads? Typically, you have a Kubernetes user who's familiar with kubectl, maybe a Kubernetes dashboard, to examine what's happening in the Kubernetes cluster and make queries about running workloads. If they want to get security information like vulnerability reports, there are lots of tools available, but they typically write results in different formats. They put those results in different places like files or databases or writing to standard out. So we thought it would be pretty great if the user didn't need to learn a whole new set of security tools to get hold of this kind of information about their Kubernetes resources. What if we could make the security reports into Kubernetes resources too, so that it's all accessible over the same Kubernetes API? And that's what we're doing with an open source project called Starboard. We've defined some Kubernetes custom resource definitions so that you can store security information within Kubernetes and access it over that same API. We've added a kubectl plugin for Starboard that allows the user to trigger security scans and vulnerability scanning, and also for other types of security report. And those security reports are associated with the resources they apply to. So if you do vulnerability scanning for a pod, you can query the vulnerability report for that pod through the Kubernetes API. And finally, we've added a Starboard Operator which watches for new pods and automatically triggers vulnerability scans for those workloads. So as new workloads get deployed, you can easily see the vulnerability information automatically created, and you can access it through the kubectl tool and Kubernetes dashboards. So let me show you a Kubernetes cluster running with the Starboard Operator, and you can see how this vulnerability information gets automatically populated and made accessible through those Kubernetes interfaces. I've got a single node EKS cluster running here, and if we take a look at the custom resource definitions, you'll see I've installed Starboard, and that has created this definition of vulnerability reports. And we can also see that the Starboard Operator is running in this cluster. So I'm already running an Nginx pod in this cluster, and if we take a look at the vulnerability reports, we can find a report associated with that Nginx pod. We can also abbreviate vulnerability report to vulns, which is much easier to type. And we can take a look at the wide output for this command, and we get a summary of the vulnerabilities that Trivy has found. can also take a look at the details of all the vulnerabilities by doing a describe on that vulnerability report. So that's how we can get all the detailed information from these Kubernetes resources. Now let's take a look at Starboard automatically generating the vulnerability reports when I install a new workload. Here I'm going to use Helm to install WordPress. I could be just running anything from YAML. Anything that results in a new pod should result in the Starboard operator generating a vulnerability report. So we can see that WordPress Helm chart has created 2 pods that are in the process of getting created. And if we take a look at the jobs that are running, we can see 2 jobs running under Starboard Operator's namespace. And those are the 2 jobs scanning the images for those 2 different pods. And if we take a look at the vulnerability reports now, we should see, in addition to the Nginx one, there are 2 new vulnerability reports for those new workloads that were created by that Helm chart. And if we take a look at the wide output, we'll get a summary of the vulnerability counts for those images as well. Here's one more aspect of Starboard that makes it easy to use. This is a screenshot from a Kubernetes dashboard called Octant. Octant is extensible, so we've built a Starboard plugin that adds additional security information into Octant's GUI. And there are other dashboards that are similarly extensible in a similar way. In this example, we're looking at an Nginx pod running in my cluster. And on the right-hand side, you can see that we've added some extra status information reporting on the number of vulnerabilities that affect this particular pod. One nice thing about storing this information as Kubernetes resources is that we can take advantage of Kubernetes native role-based access control. It's easy to set up the RBAC so that the developers working on a particular project in a particular namespace have access to the security reports for that namespace. And now that the vulnerability information is easily accessible, without them having to learn any new tools, it's easier for developers to see which dependencies they need to update and which images they need to rebuild and redeploy to lower the security risk. Check out the Starboard project and give it a try. We would love some feedback. So I've shown you today how you can use vulnerability scanning when you build an image, for regular registry scanning, for deployment checks, and in your running Kubernetes clusters. But I have said there are several scanners available, and I'd like to finish with some advice on how to choose the scanner that's best for you. Most importantly, it needs to support the Linux distribution that you use in your base images, or the multiple distributions you use. If you have a scanner that doesn't support your Linux distribution, you'll very likely see false positives because the scanner doesn't know about the patches that are applied by that distribution. Ideally, your scanner also supports the programming languages that you use. You want your scanner to update its vulnerability database frequently, ideally every day, so that you can pick up newly discovered vulnerabilities in a timely fashion. And of course, you'll be better able to use the scanner if it's easy to use and easy to integrate into your existing pipeline and tools. One aspect of this is performance. Typically, the slowest part of a scan is either downloading the image itself or downloading the vulnerability database. So you'll find some scanners can dramatically improve performance by having support for caching or for client-server configurations or lightweight databases that are fast to download for use in a CI pipeline. I want to leave you with some resources for some of the tools that I've mentioned, like Trivy and Starboard. And I've also included that link to the blog post about building a Kubernetes admission webhook. There are tons of options here for improving your application security by using vulnerability scanning. Even if all you do is turn on the basic scanning in ECR, I really hope this talk inspires you to try out some additional vulnerability scanning for your Kubernetes cluster. If you have any questions, please feel free to reach out to me. I'm Liz Rice in all the usual places online. I hope you enjoyed this talk and I hope you learned something from it. Please do go ahead and fill in that session survey with your feedback.